Welcome to Dreamy Facts. As the day gently recedes, we invite you to settle into a space of calm contemplation. Tonight, we embark on a journey through the cosmos, exploring approximately 100 fascinating facts that reveal intricate patterns, subtle wisdom, and profound beauty within the vastness of space. There is no pressure to remember or retain these details. Instead, let them unfold naturally, inviting your mind to settle into a state of peaceful curiosity. This exploration is designed to be a soothing experience, a gentle current of knowledge flowing without demanding effort or attention. We will observe the intricate dance of celestial mechanics, the subtle adaptations of planetary systems, and the quiet wisdom embedded in the universe's grand design. Each fact is a small window into the vast and interconnected tapestry of existence beyond Earth, presented in a calm and meditative tone, allowing your thoughts to drift and find stillness. Allow the gentle rhythm of these discoveries to guide you towards a state of relaxation, inviting a sense of wonder and peace as you prepare for rest. We journey through nebulae, explore distant exoplanets, and touch upon the mysteries of black holes, all while maintaining a gentle, unhurried pace. If you're finding peace in this journey, a like and subscribe helps us continue creating these restful explorations. And we're always curious. Share in the comments what city and time zone you're watching from. There's something special about knowing this experience is reaching people all over the world as they prepare for rest. As we begin our journey, we drift into the realm of the truly unexpected, where the universe defies our terrestrial understanding with its bizarre phenomena and extreme conditions. Beyond the familiar comfort of our solar system, the cosmos unfolds in ways that are both alien and profoundly captivating, inviting us to contemplate the sheer diversity of existence. We start with the fascinating concept of diamond planets, celestial bodies where carbon is so abundant and pressure so immense that entire worlds might be composed of precious gems. Research shows that 55 Cancri, an exoplanet located about 40 light-years away, is thought to be a carbon-rich world. Scientists have theorized that this planet could have a significant portion of its mass in the form of diamond, due to its high carbon content and the extreme pressures in its interior. This super-Earth orbits its star so closely that its surface temperature reaches around 4,900 degrees Fahrenheit, 2,700 degrees Celsius. The sheer density of 55 Cancri further supports the idea of heavy elements like carbon being compressed into exotic forms. Current understanding suggests that such planets form in systems where the protoplanetary disk is unusually rich in carbon and poor in oxygen, leading to the formation of carbon-based minerals rather than the silicate-based rocks common on Earth. The existence of such worlds challenges our conventional notions of planetary composition, painting a picture of cosmic opulence. Drifting further into the interstellar void, we encounter rogue planets. Worlds that wander through space without the gravitational tether of a star. These interstellar nomads are ejected from their birth systems during chaotic gravitational interactions with other planets or stars. Scientists estimate that there could be billions, or even trillions, of these free-floating planets in our Milky Way galaxy alone, potentially outnumbering stars. Research indicates that some rogue planets are thought to be Earth-sized, while others could be gas giants. The existence of these planets was largely theoretical until recent astronomical surveys began detecting candidates through gravitational microlensing events. Without a star to provide warmth, their surfaces are likely frozen and dark. Yet some researchers proposed that internal geothermal heat could potentially sustain subsurface oceans, offering a speculative environment for life. The presence of rogue planets highlights the dynamic and often violent processes that shape planetary systems. Our journey then takes us to the blistering embrace of UAT, hot Jupiters, gas giants that orbit incredibly close to their parent stars. These planets complete an orbit in just a few days, sometimes even hours, resulting in extreme temperatures that can vaporize rock. Current understanding suggests that hot Jupiters likely form further out in their planetary systems and then migrate inwards, a process known as planetary migration. One such example is WASP-12b, an exoplanet so close to its star that it is being tidally distorted into an egg shape, and its atmosphere is slowly being stripped away. The intense stellar radiation causes the atmospheres of these planets to swell, making them less dense than expected for their mass. Scientists have observed that some hot Jupiters exhibit peculiar atmospheric phenomena, such as clouds made of exotic minerals like silicates or even iron vapor, which then rain down onto the planet's surface. These worlds offer a stark contrast to the more temperate gas giants in our own solar system, showcasing the diverse outcomes of planetary evolution. Moving to another extreme, we ponder the concept of water worlds. Exoplanets believed to be entirely covered by vast deep oceans, with no visible land masses. Evidence indicates that some exoplanets, potentially in the habitable zones of their stars, might possess an abundance of water far exceeding Earth's. These worlds could have formed in the colder outer regions of their systems, accreting large amounts of ice, which then melted as they migrated closer to their stars or as their stars evolved. Researchers propose that the oceans on such planets could be thousands of miles deep, possibly extending to high-pressure ice layers at the core. The immense pressure at the bottom of these oceans could create exotic forms of ice, like Ice 7 or Ice 10, which are solid even at high temperatures. The prospect of these deep global oceans raises questions about potential life, suggesting a different kind of biosphere adapted to hydrostatic pressure and perhaps chemosynthesis rather than photosynthesis. The atmospheres of distant worlds often reveal compositions far stranger than anything found in our solar system, leading us to consider exotic atmospheres. For instance, the exoplanet HD 189733b, a hot Jupiter, is known for its deep blue colour, but this hue is not due to oceans. Instead, scientists believe it's caused by silicate particles in its atmosphere, which scatter blue light, essentially creating an atmosphere of raining glass. Other exoplanets, like the ultra-hot Jupiter K ELT9b, are so hot that heavy elements like iron and titanium vaporize in their upper atmospheres. Researchers detected iron vapor in the atmosphere of K ELT9b, indicating temperatures hot enough to dissociate molecular hydrogen. Current understanding suggests that some exoplanets could have atmospheres dominated by hydrogen cyanide or even carbon monoxide, creating conditions utterly inimical to Earth-like life but fascinating from an astrophysical perspective. These bizarre atmospheric compositions provide crucial clues about the formation and evolution of planetary systems beyond our own. Our cosmic journey now takes us to the remnants of massive stars, leading us to pulsars and neutron stars. A neutron star is the collapsed core of a massive star that has exhausted its fuel and undergone a supernova explosion. Despite being only about 12 miles, 20 kilometers in diameter, a neutron star can have a mass greater than our Sun. Scientists have observed that a single teaspoon of neutron star material would weigh approximately 6 billion tons on Earth, due to its extreme density. Pulsars are a type of rapidly spinning neutron star that emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep across space, and if one of them points towards Earth, we observe a pulse of radiation, much like a cosmic lighthouse. Some pulsars spin hundreds of times per second, rotating faster than a kitchen blender. The incredible rotational speed and immense gravitational pull of these objects make them natural laboratories for studying extreme physics. Peering into the most energetic phenomena in the universe, we encounter quasars, which are among the brightest and most distant objects known. A quasar is essentially the extremely luminous active galactic nucleus of a young galaxy, powered by a supermassive black hole accreting matter at an astonishing rate. As gas and dust spiral into the black hole, they form an accretion disk that heats up to millions of degrees Celsius, emitting vast amounts of radiation across the electromagnetic spectrum. Scientists have observed that some quasars can outshine entire galaxies, emitting more energy than 1,000 Milky Ways combined. The light from the most distant quasars has travelled billions of years to reach us, offering a glimpse into the early universe when galaxies were still forming. Current understanding suggests that quasars play a crucial role in the evolution of galaxies, as the powerful outflows of energy and matter from their central black holes can influence star formation in their host galaxies. Shifting our focus to another type of stellar remnant, we explore magnetars, which are a rare and exotic class of neutron stars characterized by incredibly powerful magnetic fields. Research shows that a magnetar's magnetic field can be thousands of times stronger than that of a typical neutron star, and quadrillions of times stronger than Earth's magnetic field. If a magnetar were located halfway between Earth and the Moon, its magnetic field would be strong enough to erase all the data on every credit card on Earth. These extreme magnetic fields are thought to be responsible for the emission of powerful bursts of X-rays and gamma rays, known as soft gamma repeaters and anomalous X-ray pulsars. Scientists have observed that the sudden release of energy from a magnetar's shifting magnetic field can cause a star quake, which can be detected across vast cosmic distances. The study of magnetars provides unique insights into the behavior of matter under the most extreme magnetic conditions imaginable. Delving into the invisible scaffolding of the cosmos, we consider dark matter halos. Vast invisible structures that are believed to surround galaxies and galactic clusters. Current understanding suggests that dark matter, which does not interact with light or other electromagnetic radiation, makes up about 27% of the universe's mass energy content, far outweighing the ordinary matter we can see. Scientists infer the existence of dark matter through its gravitational effects on visible matter, such as the rotation curves of galaxies, which show stars orbiting faster than expected based on the visible mass alone. These halos provide the gravitational quotary that holds galaxies together, preventing them from flying apart. Research indicates that the distribution of dark matter within these halos influences the formation and evolution of galaxies, acting as a cosmic scaffold upon which visible matter collects. The precise nature of dark matter remains one of the greatest mysteries in modern astrophysics, a subtle force shaping the universe from the shadows. Finally, we contemplate the immense emptiness of cosmic voids, vast regions of space that are largely devoid of galaxies, stars, and other forms of luminous matter. These voids can span hundreds of millions of light-years across, forming a network of interconnected empty spaces that make up a significant portion of the universe's large-scale structure. Scientists have observed that galaxies tend to cluster along the edges of these voids, forming a cosmic web of filaments and superclusters. Current theory suggests that voids form as a result of the gravitational pull of dark matter, which draws ordinary matter into denser regions, leaving behind these underdense expanses. The expansion of the universe also plays a role, stretching these empty regions further apart over cosmic time. While largely empty, voids are not entirely barren. They contain a few isolated galaxies and a diffuse distribution of dark matter and gas, offering a glimpse into the most desolate and expansive corners of the cosmos. As we conclude this initial exploration, we are reminded that the universe is a tapestry woven with threads of the familiar and the utterly bizarre. From planets of diamond to the invisible influence of dark matter, these cosmic oddities challenge our perceptions and expand our sense of what is possible. Each extreme environment and peculiar phenomenon underscores the universe's boundless capacity for wonder, inviting a deeper appreciation for the intricate and often startling nature of existence beyond our world. As we gently drift further, leaving behind the immediate shock of those extreme environments, we find ourselves drawn to the grand artistry of the cosmos, where invisible forces sculpt breathtaking beauty and strange, dynamic processes unfold on scales we can barely comprehend. There is a quiet majesty in how the universe continually reinvents itself, shaping and reshaping its very fabric, a continuous slow-motion ballet of creation and dissolution. Allow your mind to simply absorb these next glimpses into the universe's grand design, letting the wonder wash over you without any expectation of retention. This is merely a gentle current of knowledge, carrying you further into the tranquil expanse of space. Imagine vast, shimmering clouds of gas and dust, stretching across light-years of cosmic expanse, not as empty voids, but as the very wombs of stars. These are stellar nurseries, often appearing as majestic nebulae, like the iconic pillars of creation within the Eagle Nebula. Here, gravity, that tireless sculptor, begins its work, drawing together wisps of hydrogen, helium, and cosmic dust. Over eons, these swirling clumps grow denser, hotter, until the immense pressure ignites nuclear fusion within their cores. A new star is born, bursting forth in a blaze of light, pushing away the very clouds that cradled it. We see these nurseries as breathtaking tapestries of colour, reds from glowing hydrogen, blues from scattered starlight, and dark silhouetted forms where new worlds are still hidden, waiting for their moment to shine. It is a slow, magnificent process, a testament to the universe's ceaseless creativity, While stellar nurseries herald new beginnings, planetary nebulae mark a star's gentle farewell, a poignant and beautiful conclusion to a stellar life not unlike our own sun's eventual destiny. As a medium-sized star exhausts its core hydrogen, it swells into a red giant, shedding its outer layers into space. These expelled gases, illuminated by the star's now exposed hot core, create luminous, expanding shells that often resemble delicate iridescent bubbles or intricate cosmic sculptures. Despite their name, these nebulae have nothing to do with planets. The term arose from early telescopic observations that made them appear planet-like. Instead, they are fleeting artistic masterpieces lasting only tens of thousands of years, a blink in cosmic time, before their gases disperse into the interstellar medium, enriching it with heavier elements that will eventually form new stars and planets. We are witnessing the universe's own cycle of recycling, a graceful exhalation of stellar material. When a truly massive star reaches the end of its life, its departure is anything but gentle. It collapses under its own immense gravity, then rebounds in a cataclysmic explosion known as a supernova, briefly outshining entire galaxies. What remains is a supernova remnant, an expanding cloud of superheated gas and dust, often forming intricate filamentous structures like the Veil Nebula, the Crab Nebula. These remnants are more than just cosmic debris. They are the universe's most potent alchemical factories. The extreme temperatures and pressures within the explosion forge heavy elements: carbon, oxygen, iron, gold, and all the elements essential for life, scattering them across the cosmos. Every atom of iron in your blood, every speck of gold, was forged in the heart of a dying star. These expanding shockwaves sweep through interstellar space, compressing existing gas and dust, sometimes even triggering the formation of new stars, continuing the grand cosmic cycle. Imagine a star not peacefully orbiting its galaxy, but hurtling through the vast emptiness of intergalactic space at speeds exceeding 1,000,000 miles per hour. These are hypervelocity stars. Cosmic outcasts ejected from their galactic homes. Scientists theorize that many of these stellar speedsters gain their incredible momentum from close encounters with the supermassive black hole at the center of their galaxy. As a binary star system, or even a lone star, approaches too close, one star might be captured by the black hole's gravitational embrace, while its companion is slingshotted away, destined to wander the cosmic void alone. These celestial nomads offer a unique window into the dynamics of galactic cores and the powerful gravitational forces at play. They are the universe's ultimate adventurers, traversing the boundless ocean between galaxies, a testament to the sheer power lurking at the heart of every spiral and elliptical. The universe, in its boundless ingenuity, provides its own telescopes, bending and magnifying light from distant objects in a phenomenon known as gravitational lensing. According to Einstein's theory of general relativity, massive objects, like galaxies or clusters of galaxies, warp the fabric of space-time around them. When light from a more distant galaxy passes near such a massive foreground object, its path is bent, much like light passing through a glass lens. This bending can magnify, distort, or even create multiple images of the background object, allowing us to see galaxies that would otherwise be too faint or too far away to detect. We use these natural cosmic lenses to peer back further in time, observing the very first galaxies, or to detect distant exoplanets by the subtle distortions they create. It is a profound demonstration of gravity's reach, transforming the immense weight of galaxies into a tool for cosmic discovery. Beyond individual galaxies and clusters, the universe is structured on an even grander scale, forming what scientists call the cosmic web. Imagine an invisible scaffolding, a vast intricate network of filaments and knots interspersed with immense, nearly empty voids. Galaxies are not randomly scattered throughout space. Rather, they cluster along these long, thin filaments, like pearls on a string, and congregate in massive nodes where these filaments intersect. The voids, on the other hand, are the vast dark spaces, hundreds of millions of light years across, containing very few galaxies. This enormous structure is believed to have been shaped by the interplay of dark matter and dark energy over billions of years, with dark matter providing the gravitational force that pulled ordinary matter into these colossal formations. It is the universe's largest known structure, a breathtaking testament to the subtle forces that have woven the fabric of reality into its current sprawling form. When we think of volcanoes, we typically imagine molten rock and scorching lava. Yet, in the cold, distant reaches of our solar system and beyond, a different kind of volcanic activity occurs: cryovolcanism, or ice volcanoes. On moons like Neptune's Triton or Saturn's Enceladus, instead of erupting silicate rock, these volcanoes spew out volatile substances like water, ammonia, methane, or nitrogen, often in a geyser-like fashion. On Enceladus, for instance, powerful jets of water vapor and ice particles erupt from fissures near its south pole, hinting at a subsurface ocean warmed by tidal forces. These eruptions contribute to Saturn's E-ring and offer tantalizing clues about the potential for life in these icy, outer worlds. It is a startling reminder that geological processes can manifest in incredibly diverse and unexpected ways across the cosmic landscape, transforming our understanding of what constitutes a 6 or a 7. While many planets possess rings, none are as spectacularly intricate and mesmerizing as those surrounding Saturn, a true jewel of our solar system. These magnificent structures, stretching hundreds of thousands of miles across but often no more than a few hundred feet thick, are not solid but are comprised of billions of individual particles, ranging from microscopic dust grains to house-sized boulders. Composed primarily of water ice, with a smattering of rocky material, these particles endlessly orbit Saturn, each following its own path, creating a celestial ballet of countless tiny moons. The precise origins of Saturn's rings remain a subject of active research, with theories ranging from the breakup of a shattered moon to the remnants of comets or asteroids. Their delicate beauty and complex dynamics, sculpted by the gravitational tugs of Saturn's many moons, offer a constant source of wonder and a reminder of the universe's capacity for breathtaking, enduring artistry. Invisible yet immensely powerful, magnetic fields permeate the cosmos, shaping everything from the gentle flow of the solar wind to the violent outbursts of distant stars. One of the most dynamic processes involving these fields is magnetic reconnection, an explosive event where oppositely directed magnetic field lines suddenly break and then reform, releasing vast amounts of energy. On our own Earth, this phenomenon is responsible for the dazzling auroras, the northern and southern lights, as charged particles from the sun are funneled along Earth's magnetic field lines, exciting atmospheric gases. On the sun, magnetic reconnection drives powerful solar flares and coronal mass ejections, sending bursts of radiation and plasma hurtling into space. It is a fundamental process in astrophysics, an unseen dance of energy that sculpts plasma, drives stellar activity, and illuminates the skies of planets, a testament to the elegant, powerful forces at play in the universe. Among the most profound discoveries in cosmology is the cosmic microwave background, CMB, a faint glow of radiation that permeates the entire universe. This isn't starlight or galaxy light. Rather, it is the residual heat from the Big Bang itself, the very first light emitted when the universe was only about 380,000 years old. Before this time, the universe was a superheated, opaque plasma, too hot for light to travel freely. As it expanded and cooled, electrons and protons finally combined to form neutral atoms, allowing photons to escape and stream across the cosmos. This ancient light, stretched and cooled by billions of years of cosmic expansion, now appears as microwaves. The CMB provides an invaluable snapshot of the early universe, revealing tiny temperature fluctuations that represent the seeds from which all galaxies and clusters eventually grew. It is the universe's oldest light, a gentle echo of creation, whispering tales of its infancy. Deep within the cosmic web, approximately 250 million light-years away, lies a region of space known as the Great Attractor. This mysterious gravitational anomaly exerts an immense pull on our own Milky Way galaxy and thousands of other galaxies within a vast supercluster called Laniakea, drawing them towards it at millions of miles per hour. While we can observe its gravitational influence, the exact nature of the Great Attractor remains largely obscured by the quote 8, a region of the sky heavily obscured by the dust and gas within our own Milky Way, making it difficult to observe invisible light. Scientists theorize it is likely a massive, diffuse concentration of dark matter and galaxies, perhaps an incredibly dense supercluster whose gravitational dominance is shaping the large-scale flow of galaxies in our cosmic neighborhood. It is a powerful, unseen hand, subtly guiding the dance of galaxies across unimaginable scales, a testament to the universe's enduring mysteries. As we gently recede from these profound and often startling phenomena, you may find a quiet sense of the universe's intricate design settling within your mind. We have journeyed through the dynamic processes of star birth and death, witnessed the invisible forces that sculpt light and matter, and peered into the very echoes of creation. There is no need to grasp every detail, only to absorb the expansive feeling of wonder that these cosmic facts evoke. Allow this gentle current to carry you further into the vast, serene ocean of space, where even more wonders await your tranquil contemplation. As we gently recede from the veiled mystery of the Great Attractor, that colossal, unseen hand guiding galaxies across vast cosmic distances, our journey continues into the subtle, yet profound, forces that shape the very fabric of existence. We now turn our gaze towards energies and phenomena that, though often invisible, orchestrate the grandest cosmic ballets and whisper through the deepest currents of time, inviting you to simply listen, to absorb, and to let your mind wander through the boundless expanse. Imagine an invisible, pervasive force, not pulling things together like gravity, but subtly yet relentlessly pushing them apart. This is the enigma we call dark energy. While gravity, that familiar sculptor of stars and galaxies, works to draw matter inward, dark energy acts as a cosmic accelerant, causing the expansion of the universe to speed up, not slow down. It's a profound paradox, a mystery that currently eludes our full comprehension, yet it constitutes an astonishing 68% of the universe's total energy density. Scientists theorize that it might be an inherent property of space itself, an energy that emerges as new space is created, forever increasing its influence as the universe expands. Contemplating dark energy is to ponder the very destiny of the cosmos, an ultimate push towards an ever larger, ever emptier expanse, a gentle yet inexorable expansion into eternity. If the universe were a vast, serene pond, then the most violent cosmic events, the collision of black holes, the spiraling dance of neutron stars, the cataclysmic bursts of supernovae, would send ripples across its surface. These ripples are gravitational waves, undulations in the very fabric of space-time itself, travelling at the speed of light. For centuries, they were merely a prediction of Einstein's theory of general relativity, an elegant whisper in the equations. Yet, in recent years, instruments like LIGO and Virgo have become sensitive enough to detect these incredibly faint tremors, opening an entirely new window onto the universe. We are now able to quote 9 the universe's most profound and energetic events, sensing the warping and stretching of space and time directly. It is like gaining a new sense, allowing us to perceive the universe not just through light, but through the very vibrations of its existence, a deep hum from the cosmic orchestra. Among the universe's most spectacular, yet fleeting phenomena are gamma-ray bursts, GRBs. These are the most powerful explosions known, brief, intense flashes of high-energy gamma radiation that can outshine entire galaxies for a few precious seconds or minutes. Imagine a cosmic lighthouse, not steadily beaming, but flaring with an intensity that speaks of ultimate destruction and creation. Scientists believe that long GRBs, lasting more than 2 seconds, are often born from the collapse of massive, rapidly rotating stars into black holes, while shorter bursts may arise from the collision and merger of 2 neutron stars. These events are so energetic that a single GRB can release more energy than our Sun will produce over its entire 10 billion year lifetime. They are cosmic fireworks, seen across billions of light years, providing us with glimpses into the most extreme physics in the universe, a testament to the raw, untamed power that sculpts the cosmos. We often picture black holes as the anchors of galaxies, residing at their hearts or orbiting within their stellar families. Yet, the cosmos holds another more solitary class, rogue black holes. These are stellar mass black holes, born from the collapse of massive stars that have been violently ejected from their home galaxies or star systems, perhaps by a gravitational slingshot effect during a chaotic multi-star interaction, or a powerful supernova kick. They wander the vast empty stretches of intergalactic space, unseen and unattached, their presence revealed only by the subtle bending of light from background stars as they pass by, a phenomenon known as microlensing. Imagine these silent predators drifting through the cosmic darkness, their immense gravitational pull an invisible trap for any unfortunate star or gas cloud that crosses their path. They are a reminder of the universe's inherent dynamism, where even the most fundamental structures can become unbound, journeying through the void in profound isolation. As we contemplate the grand scale of galaxies, we often envision them as stable, majestic spirals or ellipses. Yet, The universe is a place of constant transformation, and evidence of this dynamism can be seen in the ethereal beauty of stellar streams. These are long ribbon-like structures of stars stretching for thousands of light years that are the ghostly remnants of smaller dwarf galaxies or globular clusters that have been gravitationally torn apart by the immense tidal forces of a larger galaxy, such as our own Milky Way. Imagine a celestial dance where the larger partner slowly, gracefully, yet inexorably, pulls apart its smaller companion, scattering its stars into a beautiful elongated trail. These streams provide vital clues about the history of galactic mergers and the distribution of dark matter within galaxies, painting a picture of cosmic cannibalism that, paradoxically, contributes to the growth and complexity of the larger structures. They are the universe's own cosmic tears, shed in a slow, majestic process of galactic assimilation. For millennia, our understanding of space was confined to the objects gravitationally bound to our Sun, but in recent years a new class of celestial traveller has captivated our imagination. Interstellar objects. These are comets or asteroids that originated in other star systems, having been ejected from their birthplaces to wander the vast interstellar medium for potentially billions of years, until, by chance, their paths intersected with our own solar system. The first confirmed interstellar visitor, Oumuamua, discovered in 2017, was an elongated, dark object moving at an incredible speed, its trajectory betraying its extrasolar origins. It was followed by Borisov, a more conventional comet, but equally a guest from afar. These objects are cosmic nomads, silent messengers from distant star systems, carrying with them pristine material from other stellar nurseries. Their fleeting passage through our solar system offers us a rare, direct glimpse into the diverse compositions and dynamics of planetary systems far beyond our own, a gentle reminder of the boundless exchange happening across the galaxy. Even as we sit here, bathed in the warmth of our sun, we are constantly being permeated by an invisible, high-energy rain from space, cosmic rays. These are not rays of light, but rather atomic nuclei, mostly protons and electrons, accelerated to incredible speeds, sometimes approaching the speed of light, by some of the most violent events in the cosmos. Their origins are diverse and still partly mysterious, with supernovae, active galactic nuclei, and other extreme astrophysical phenomena believed to be their primary accelerators. As these energetic particles hurtle through space, they collide with Earth's atmosphere, creating showers of secondary particles that can reach the ground. They are a constant, silent bombardment, a fundamental part of the cosmic environment, influencing everything from atmospheric chemistry to the faint background radiation of our planet. Contemplating cosmic rays is to acknowledge the omnipresent energy flowing through the universe, an unseen force that connects our small world to the grand, energetic processes of distant galaxies. As our journey nears its gentle close for this chapter, let us expand our contemplation to the ultimate frontier of theoretical physics, the multiverse. This mind-bending concept posits that our universe, with all its stars, galaxies, and cosmic wonders, might not be the only one. Instead, it could be just one of an infinite number of universes, each with its own unique set of physical laws, dimensions, and histories. Imagine a vast cosmic ocean, teeming with countless bubble universes, or perhaps an infinite tapestry where every conceivable possibility plays out in a parallel reality. While still a realm of theory and intense scientific debate, the multiverse arises from various cosmological models, offering solutions to profound questions about the fine-tuning of our own universe. It is a concept that pushes the boundaries of imagination, inviting you to consider that the wonders we have explored, vast as they are, might be but a single drop in an immeasurable sea of existence. As we gently drift from the precipice of this infinite possibility, remember that the universe continues its unending dance, a symphony of visible and invisible forces, of known wonders and profound mysteries. We invite you to carry these images, these whispers of cosmic knowledge, with you, allowing them to settle into the quiet corners of your mind. There is no need to grasp or hold on to them tightly. Simply let them be, a soothing current of wonder flowing through your thoughts, a gentle reminder of the boundless beauty that surrounds us, both near and impossibly far. As our journey through the cosmic tapestry gently unfolds, we find ourselves at the precipice of yet another profound revelation. Having contemplated the vast, perhaps infinite possibilities of a multiverse, we now turn our gaze inward towards the more subtle yet equally astonishing facets of our own universe. Here, the boundaries blur, the familiar becomes strange, and the very fabric of existence reveals its intricate, often hidden dance. We invite you to drift further into this tranquil exploration, allowing the gentle current of knowledge to carry you through realms where stars refuse to ignite, where time itself stretches and warps, and where the universe whispers its deepest secrets through enigmatic signals and complex chemistry. Let us delve into the quiet majesty of these unseen wonders, appreciating the delicate balance and astonishing diversity that defines our cosmos. Imagine a celestial body caught in an eternal twilight, a true cosmic paradox that hovers between the grandeur of a star and the solitude of a planet. These are the thin, brown dwarfs, often referred to as failed stars. Unlike true stars, which possess enough mass to ignite and sustain hydrogen fusion in their cores, brown dwarfs are not quite massive enough. They fall short of that critical threshold, never reaching the internal temperatures and pressures required to become shining beacons. Instead, they glow with a dim, reddish light, slowly fading over billions of years as they radiate away the residual heat from their formation and fused deuterium, a heavier isotope of hydrogen, for a brief period. These enigmatic wanderers are challenging to detect, cloaked in their subtle luminescence, yet they represent a significant population in our galaxy, bridging the gap between the colossal gas giants like Jupiter and the smallest, most timid stars. Their very existence reminds us that the universe delights in blurring categories, presenting a spectrum of possibilities that continually expands our understanding of cosmic evolution. From the almost stars, we turn our attention to the universe's most common and longest-lived inhabitants, the red dwarfs. These diminutive stars, typically less than half the mass of our Sun, burn their nuclear fuel at an incredibly slow and efficient rate. While they may lack the fiery brilliance of larger stars, their longevity is unparalleled, often projected to shine for trillions of years, far longer than the current age of the universe. This makes them incredibly stable, a gentle, consistent presence in the cosmic night. Planets orbiting red dwarfs would experience a perpetual reddish glow, a subdued warmth compared to our Sun's golden embrace. Scientists ponder these quiet giants with great interest, as their abundance and extreme lifespan suggest they could host a vast number of potentially habitable worlds. Yet, their proximity to their stars also means planets in their habitable zones might be tidally locked, presenting a world of eternal day on one side and endless night on the other, a mesmerizing, if challenging, environment for the emergence of life. In the ancient, tightly packed communities of globular clusters, where stars are expected to age gracefully and predictably, we encounter a fascinating anomaly: the blue stragglers. These stars defy their apparent age, appearing younger and bluer than their stellar neighbours, which should have long since evolved into red giants or white dwarfs. It's as if they've discovered a cosmic fountain of youth. Current understanding suggests these stellar rebels achieved their extended youth by straggling behind the normal evolutionary sequence, often through gravitational interactions. They might siphon off hydrogen fuel from a close companion star, rejuvenating themselves in a process known as mass transfer. Or perhaps they are the product of two smaller stars merging into a single, more massive and thus bluer and hotter star. These celestial anomalies offer a vivid testament to the dynamic and often surprising interplay of gravity and stellar evolution, reminding us that even in the most well-ordered cosmic neighborhoods, unexpected dramas are always unfolding. Our journey has already introduced us to the unimaginable density of neutron stars, where matter is compressed to a degree that defies earthly comprehension. But what if the universe holds secrets of even more exotic states? Theoretical physics whispers of strange matter and quark stars. Within the crushing gravity of a neutron star, protons and neutrons are squeezed so tightly that their constituent quarks, up and down quarks, might deconfine, forming a fluid-like state of quark matter. Some theories propose that under even more extreme conditions, or perhaps within the cores of the most massive neutron stars, this quark matter could transform into strange matter, a hypothetical form of matter containing strange quarks in addition to up and down quarks. If strange matter is truly stable, it could lead to the existence of quark stars, or even strange stars, objects composed predominantly of this exotic substance, making them even denser and more compact than their neutron star counterparts. These concepts push the very limits of our understanding of matter, inviting us to contemplate the profound and often bizarre possibilities that lie hidden within the heart of cosmic behemoths. As we navigate the universe's extremes, we are inevitably drawn to the profound insights offered by Einstein's theory of relativity, particularly the concept of time dilation. This isn't merely a theoretical construct, it's a verified reality, where time itself is not an absolute, unwavering constant, but a flexible dimension that can stretch and contract. The stronger the gravitational field, or the faster an object moves, the slower time passes for that object, relative to an observer in a weaker gravitational field or moving at a slower speed. Near the event horizon of a black hole, for instance, time would appear to slow to an almost complete stop for an infalling observer, while to a distant observer, that same individual would seem to take an eternity to cross the threshold, their image eventually freezing and fading. This mind-bending phenomenon reveals that our perception of time is deeply intertwined with the very fabric of space-time, reminding us of the universe's capacity to bend not just light and matter, but the very rhythm of existence itself. Extending our appreciation for the elastic nature of space-time, we encounter another astonishing consequence of massive rotating objects: frame dragging. Imagine space-time as a vast invisible ocean. Now, picture a colossal, rapidly spinning object, like a neutron star or a black hole churning within this ocean. According to Einstein's general relativity, such a spinning mass doesn't just curve space-time, it drags it along with its rotation, creating a sort of cosmic eddy or vortex, anything from light to matter. Passing through this swirling region of space-time would be subtly, yet irresistibly, tugged in the direction of the object's spin. This effect is most pronounced near the most extreme rotators in the universe, such as rapidly spinning black holes, where the space-time around them is so dramatically twisted that it forms a region called the ergosphere, from which it's theoretically possible to extract energy. Frame dragging is a subtle, yet profound demonstration of how intimately gravity and motion are interwoven with the very structure of the universe, revealing a dynamic and responsive cosmic canvas. Our exploration of the cosmos often relies on direct observation, but sometimes the most profound discoveries are made through indirect, almost ghostly means. Cosmic microlensing is one such technique, a subtle yet powerful method that allows us to detect objects that are otherwise invisible to our telescopes. It harnesses the power of gravity, specifically the way massive objects bend and magnify the light from more distant background stars. When an unseen object, perhaps a rogue planet, a brown dwarf, or even a distant exoplanet orbiting a far-off star, passes precisely in front of a background star from our perspective, its gravitational field acts like a temporary magnifying glass. This causes the background star to brighten and then dim in a very specific, predictable pattern. By meticulously analyzing these fleeting shifts in brightness, astronomers can infer the presence and even the mass of the intervening, otherwise undetectable object. It is a testament to the universe's intricate design, where the very bending of light becomes a tool for unveiling hidden worlds, expanding our census of planetary systems beyond our immediate stellar neighborhood. From the subtle bending of light, we shift our attention to some of the universe's most perplexing and powerful mysteries: fast radio bursts, FRBs. These are incredibly intense millisecond-long flashes of radio waves originating from distant galaxies, carrying as much energy in that fleeting instant as our sun emits in tens of thousands of years. Their origins remain one of the most compelling unresolved mysteries in astrophysics. While some FRBs have been observed to repeat, allowing astronomers to pinpoint their galactic homes and even identify the likely source as a magnetar, many are one-off events, leaving scientists to ponder a wider array of potential culprits. Could they be the catastrophic aftermath of colliding neutron stars, or perhaps the final death throes of a supermassive black hole devouring a star? The sheer power and brevity of these bursts, coupled with their vast distances, paint a picture of an active, often violent and profoundly enigmatic universe, constantly broadcasting signals we are only just beginning to decode. Each burst is a cosmic exclamation mark, a momentary beacon from the deep, inviting us to further unravel the secrets of extreme astrophysical phenomena. As we journey through the seemingly empty expanse between stars, it is easy to imagine a desolate vacuum, yet the reality is far more vibrant, brimming with a complex and surprising chemistry. we encounter interstellar molecules, a vast array of organic and inorganic compounds floating within the cold, dense clouds of gas and dust that permeate galaxies. These cosmic chemistry sets are not merely simple atoms, but include intricate molecules like water, carbon monoxide, ammonia, and even complex organic compounds like alcohols and sugars. These molecules form through intricate reactions on the surfaces of dust grains or in the gas phase, shielded from destructive stellar radiation. The presence of these complex building blocks in such abundance suggests that the raw ingredients for life are not unique to Earth, but are widely distributed throughout the universe. It is a profound realization, hinting that the intricate dance of chemistry, capable of forming the very foundations of biological systems, is a fundamental process woven into the fabric of the cosmos, silently preparing the stage for life's potential emergence across countless worlds. While space is largely a vacuum and cannot transmit sound as we know it on Earth, the universe does possess its own unique form of acoustic phenomena, particularly within the vast hot plasma of galaxy clusters. Here we encounter what might be metaphorically described as the cosmic hum. Supermassive black holes at the centers of these clusters periodically erupt, unleashing powerful jets and bubbles of hot gas. These colossal outbursts generate pressure waves, akin to sound waves, that ripple through the surrounding plasma. Although these waves are at frequencies far too low for human ears to perceive, billions of times lower than the lowest note on a piano, they carry immense energy, preventing the hot gas from cooling and collapsing to form new stars. This hum is a testament to the ongoing violent interplay between supermassive black holes and their galactic environments, shaping the evolution of clusters over cosmological timescales. It's a silent symphony of cosmic power, a low-frequency rumble that underscores the dynamic and interconnected nature of the universe, a continuous, powerful echo in the void. As we gently recede from these profound insights, we hope you feel a heightened sense of wonder, a deeper connection to the intricate workings of the universe. From the failed stars to the silent hum of galaxy clusters, each fact offers a glimpse into the boundless creativity and complexity of existence. These are not merely isolated phenomena, but threads in a grand cosmic tapestry, revealing the subtle forces and hidden depth that continually challenge and expand our understanding. May this tranquil journey continue to inspire a quiet awe, a peaceful contemplation of the vast and beautiful unknown that still awaits our discovery. As that profound, low-frequency hum gently recedes into the background of our cosmic journey, we invite you now to drift further, deeper, into the universe's astonishing tapestry. We've explored the whispers and the hidden depths, but there are still grander architectures and more subtle, yet equally profound extremes awaiting our gentle gaze. Let us now turn our attention to the universe's colossal ballets, its oldest echoes, and the quiet, monumental transformations that unfold over eons, each revealing another layer of the cosmos's magnificent design. Imagine the slow, majestic dance of colossal islands of stars, each containing billions upon billions of suns, drawing inevitably closer. This is the reality of galactic cannibalism, a process where larger galaxies, exerting an irresistible gravitational pull, slowly but surely absorb smaller galaxies. It's not a sudden, violent collision in the way we might picture, but rather a drawn-out gravitational embrace that can span hundreds of millions, even billions of years. As a smaller galaxy is drawn in, its stars, gas and dust are gradually stripped away, becoming incorporated into the larger entity, often creating spectacular tidal tails of stars that stretch out into the void. Our own Milky Way is no stranger to this cosmic feast. Evidence suggests it has consumed several smaller galaxies in its history, and is currently in the process of consuming the Sagittarius dwarf spheroidal galaxy. These events are fundamental to galactic evolution, shaping the colossal structures we observe today, quietly building the universe's grandest cities, one star system at a time. It's a testament to the universe's constant state of flux, where even the most immense structures are subject to an endless cycle of merging and transformation. Beyond the gentle glow of nebulae and the serene spin of galaxies, the cosmos is also home to incredibly powerful, almost unfathomable phenomena. Among these are hyper-energetic cosmic rays, particles, mostly protons and atomic nuclei, that travel through space with energies far exceeding anything we can produce in terrestrial accelerators. These are not rays of light, but high-speed subatomic projectiles, accelerated to nearly the speed of light by some of the universe's most violent events. Scientists theorize their origins lie in extreme cosmic environments, perhaps the shock waves from supernovae, the powerful jets emanating from active galactic nuclei, or the crushing gravitational fields around supermassive black holes. When these particles strike Earth's atmosphere, they create cascades of secondary particles that can be detected. Their immense energy and the vast distances they traverse before reaching us make them profound messengers from the universe's most energetic corners, carrying whispers of processes that defy our everyday understanding, reminding us of the raw, untamed power that permeates the void. As we contemplate such destructive forces, let us also consider transformations of exquisite, quiet beauty. We've previously touched upon white dwarfs, the dense, Earth-sized remnants of stars like our Sun. Over unimaginable spans of time, these stellar embers continue to cool, slowly radiating away their residual heat. For some white dwarfs, particularly those with carbon-oxygen cores, this cooling process leads to an extraordinary transformation, white dwarf crystallization. As the temperature drops, the nuclei within the white dwarf's core begin to arrange themselves into a crystalline lattice. Much like how water freezes into ice or carbon atoms form a diamond, this means that deep within these ancient stellar husks, entire planets' worth of matter could solidify into a giant cosmic diamond. This process is incredibly slow, taking trillions of years, far longer than the current age of the universe. Yet the evidence for such crystallization is supported by observations of cooling rates and seismic studies of white dwarfs. It's a breathtaking thought, a star, once a fiery beacon, slowly solidifying into a colossal glittering gem, a silent monument to stellar evolution, patiently waiting in the cosmic dark. Our journey has taken us to distant galaxies and exotic exoplanets, but let us now return to the quiet, frigid fringes of our own solar system. Far beyond the orbit of Neptune, stretching perhaps a quarter of the way to the nearest star, lies the Oort cloud. This vast spherical shell of icy debris is thought to be the birthplace of most long-period comets, those majestic wanderers that occasionally grace our inner skies. Composed of billions, perhaps trillions of icy planetesimals, the Oort cloud is a remnant from the very formation of our solar system, a fossilized record of its earliest days. It is a region of profound cold and darkness, where the sun is merely a bright star among countless others, its warmth and light barely reaching these distant icy bodies. Occasionally, a passing star or the gravitational tug of the Milky Way can perturb these icy residents, sending some hurtling inwards towards the sun, beginning their long luminous journey. The Oort cloud represents the true immense boundary of our solar system, a silent, swirling reservoir of primordial ice, an unseen guardian at the gates of interstellar space. From the serene edge of our solar system, we journey inward to a more dynamic, energetic display. Consider Io, one of Jupiter's largest moons, a world of ceaseless volcanic activity, constantly reshaped by the immense tidal forces exerted by its colossal parent planet. The material ejected from Io's hundreds of volcanoes, sulfur dioxide, sulfur and other gases, does not simply fall back to the moon's surface. Instead, much of it escapes into space, forming a donut-shaped cloud of gas that orbits Jupiter. As this material is ionized by solar radiation and Jupiter's powerful magnetic field, it creates the plasma torus of Io. This glowing, energetic ring of plasma is an incredible sight, a vibrant, electrically charged halo that encircles Jupiter, radiating intensely in ultraviolet light. It's a continuous, dynamic process, where Io's fiery internal engine fuels a vast luminous structure that dwarfs the moon itself. The plasma torus is a testament to the interconnectedness of celestial bodies, where the internal heat of a moon can sculpt a luminous, planetary scale feature, a constant, silent electrical current flowing through the Jovian system. From the slow dance of galaxies and the steady glow of plasma, let us now contemplate objects that push the very limits of rotation. We've explored pulsars before, the rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses. But a special class, known as millisecond pulsars, takes this phenomenon to an extreme. These incredibly dense stellar remnants can rotate hundreds, even over 1,000 times per second, their surfaces moving at a significant fraction of the speed of light. To put this in perspective, a point on their surface could be travelling faster than the Earth orbits the Sun. Scientists believe these pulsars achieve such dizzying speeds by, quote, 17 on a companion star in a binary system. As matter from the companion falls onto the neutron star, it spins up the pulsar, much like a child pushing a merry-go-round faster and faster. The precise, rhythmic pulses from these cosmic speed demons make them invaluable tools for astronomers, used as incredibly accurate cosmic clocks to test theories of gravity and even search for gravitational waves. They are a vivid demonstration of the extreme physics that governs the universe's most compact objects. Our journey often brings us to the present-day universe, but let us now peer back in time, to the very earliest moments after the Big Bang, to a state of matter so extreme it existed only fleetingly. In the first microseconds of the universe's existence, the temperatures and densities were so immense that matter could not form into ordinary protons and neutrons. Instead, the universe was a superheated primordial soup known as quark-gluon plasma. In this exotic state, quarks, the fundamental building blocks of protons and neutrons, and gluons, the particles that bind them together, existed freely, unbound by the strong nuclear force that usually keeps them confined within larger particles. It was a universe without atoms, without nuclei, just a sea of fundamental particles interacting freely. While this state existed for only a tiny fraction of a second in the early cosmos, scientists can recreate it momentarily in powerful particle accelerators on Earth, smashing heavy ions together at incredible speeds. These fleeting recreations offer a precious glimpse into the universe's infancy, helping us understand the fundamental forces and particles that ultimately shaped everything we see around us today. Just as individual stars can be ejected from their galactic homes, entire galaxies can also find themselves cast out into the desolate intergalactic void. These are runaway galaxies, majestic islands of stars that have been violently ejected from their galaxy clusters due to intense gravitational interactions, often during close encounters with other massive galaxies or the merger of two clusters. Picture a cosmic game of billiards on the grandest scale, where the immense gravitational forces can slingshot an entire galaxy away from its cosmic companions. Once ejected, these runaway galaxies become solitary travelers, drifting through the vast emptiness of intergalactic space, far from the bustling hubs of galaxy clusters. They carry their billions of stars, their nebulae, and their dark matter halos with them, a lonely procession across the cosmic stage. Their existence highlights the dynamic and sometimes chaotic nature of galaxy clusters, where even the most colossal structures can be subjected to gravitational forces powerful enough to send entire stellar cities on an irreversible journey into the profound silence of the cosmic abyss. As we conclude this chapter, let us zoom out to the grandest scale of all, to witness the universe's ultimate architectural design. We've spoken of galaxies and clusters, but these are merely components of even vaster formations. Superclusters are the largest known gravitationally bound structures in the universe, colossal assemblages of thousands of galaxies, spanning hundreds of millions of light-years. These superclusters are not randomly scattered, but are themselves organized into an even more intricate pattern. The cosmic web. Imagine an immense three-dimensional web, with superclusters forming the dense nodes and long, thin strands of galaxies and dark matter, known as filaments, connecting them. In between these filaments and nodes lie vast, empty regions called cosmic voids. This frothy, sponge-like structure, shaped primarily by the invisible scaffolding of dark matter, dictates the distribution of all visible matter in the universe. It is the universe's largest known architecture, a breathtaking display of cosmic engineering on a scale that humbles and inspires, revealing a universe that is both intricately organized and boundlessly expansive. As these grand designs and extreme states of matter gently settle in your mind, we hope you feel a renewed sense of the universe's boundless creativity and its quiet, constant evolution. Each fact, a tiny facet of an unimaginable whole, invites you to simply observe, to wonder, and to let the gentle current of cosmic knowledge carry you further into peace. Our journey together continues, always unfolding new layers of this magnificent, mysterious cosmos, always inviting you to simply be. We have journeyed through realms of unimaginable density and light, witnessed the grand artistry of stellar cycles, and felt the subtle push and pull of cosmic forces. Now, as our exploration deepens, we invite you to listen for the faint whispers carried across unimaginable distances, signals from the universe's most energetic phenomena, echoes from its earliest moments, and even theoretical blueprints of what advanced life might achieve. Close your eyes or let your gaze soften as we continue to drift through this gentle current of knowledge where every revelation is an invitation to profound wonder and quiet contemplation. Imagine not just a powerful beacon, but one aligned perfectly with your line of sight, its beam piercing across billions of light years with astonishing intensity. These are blazars, a particularly potent type of quasar, which we have briefly encountered before. Here, the supermassive black hole at the heart of a distant galaxy is not merely devouring matter, but is also launching two colossal jets of plasma, accelerated to nearly the speed of light, perpendicular to its accretion disk. What makes a blazar so unique, so incredibly luminous in our sky, is the precise orientation of one of these relativistic jets directly towards us. It's like looking straight down the barrel of a cosmic particle accelerator. The light from these jets, amplified and beamed, can outshine the entire galaxy they reside in, dominating the electromagnetic spectrum from radio waves to gamma rays. This direct orientation means blazars exhibit rapid and dramatic variability in brightness, flaring up unpredictably, as if the universe itself is winking at us with an eye of pure energy. Studying these cosmic searchlights offers us a rare direct window into the extreme physics of black hole, accretion, and jet formation, revealing processes that defy our earthly intuition, yet shape the very fabric of distant galaxies. Consider planets that dance so intimately with their parent stars that one side is perpetually bathed in searing daylight, while the other remains locked in an endless frigid night. These are tidally locked worlds, a common fate for exoplanets, orbiting close to their stars, particularly red dwarfs. On such a planet, the gravitational embrace of its star has slowed its rotation until one hemisphere always faces the star, much like our moon always shows the same face to Earth. The implications for these worlds are profound and bizarre. The day side might be a desolate, blistering inferno where liquids boil away and rocks melt under the relentless glare. The night side, conversely, would be a frozen wasteland, plunged into eternal darkness. However, between these two extremes lies a fascinating, potentially habitable, quote, 18, a band of perpetual twilight. Here, where the star hangs low on the horizon, temperatures might be moderate enough for liquid water, and fierce winds, born from the dramatic temperature gradient between the two hemispheres, could ceaselessly howl, redistributing heat and sculpting alien landscapes. These worlds challenge our Earth-centric notions of habitability, inviting us to imagine life evolving in the most extraordinary and unforgiving of cosmic cradles. In our journey, we've encountered light, gravitational waves, and even the faint hum of the Big Bang. Now let us consider the most elusive of cosmic messengers, neutrinos. These subatomic particles are often called ghost particles for a good reason. They interact so weakly with matter that billions of them pass through your body every second, utterly undetected. Born from the most violent and energetic events in the universe, supernovae explosions, the fusion reactions in stars like our Sun, and even the fiery hearts of active galaxies, neutrinos carry information directly from these extreme environments without being absorbed or scattered. Unlike photons, which can be blocked by dense gas and dust, neutrinos escape almost unimpeded, travelling across vast cosmic distances. By building colossal detectors deep underground or submerged in ice, shielding them from other cosmic radiation, scientists are slowly beginning to capture these ghostly particles. Each detection offers a fleeting glimpse into the universe's most hidden processes, allowing us to quote 20 beyond the veil of light, directly into the furnace of stellar collapse or the energetic cores of distant blazes. They are the universe's silent couriers, whispering tales of cosmic violence and transformation from the very edges of existence. Just as archaeologists meticulously unearth artifacts to reconstruct ancient civilizations, astronomers engage in stellar archaeology to unravel the history of galaxies. Our own Milky Way, a majestic spiral, is not a static entity but a dynamic tapestry woven from countless past events. By observing the motion, chemical composition, and ages of individual stars, particularly those in the galactic halo or in stellar streams, we can trace the ancient pathways of stellar populations. These stars act as living fossils, their properties bearing the imprint of their birth environments and subsequent journeys. For example, some stars in our halo are remnants of smaller dwarf galaxies that were long ago cannibalized by the Milky Way. Their distinct chemical signatures, often poorer in heavy elements than younger stars, betray their extragalactic origins. The discovery of stellar streams, vast rivers of stars that were once part of these swallowed galaxies, provides direct evidence of these cosmic mergers. Through this meticulous work, we are slowly piecing together a grand narrative of galactic formation and evolution, understanding how our home galaxy grew over billions of years, absorbing smaller companions and shaping its intricate spiral arms from the scattered stardust of cosmic collisions. It's a profound testament to the universe's endless cycle of creation and destruction, written in the very stars themselves. Before the universe glowed with the familiar light of countless galaxies, there was an epoch known as the Cosmic Dawn, a period of profound darkness that followed the Big Bang and the cooling of the cosmic microwave background. For hundreds of millions of years, the universe was a vast, cold expanse of neutral hydrogen and helium gas, devoid of stars and galaxies. Then, approximately 100 to 200 million years after the Big Bang, gravity began to pull together the densest pockets of this primordial gas. From these collapsing clouds, the very first stars were born, gargantuan, short-lived, and incredibly luminous population 3 stars, composed almost entirely of hydrogen and helium, as heavier elements had yet to be forged. These pioneering stars and the first nascent galaxies they formed began to ionize the neutral hydrogen gas, heating it up and making it transparent to light once more. This epoch of reionization marked the end of the cosmic dark ages and heralded the cosmic dawn, illuminating the universe and setting the stage for the formation of the galaxies and structures we observe today. It's a period of intense scientific inquiry, where current telescopes are pushing the boundaries of observation to capture the faint red-shifted light from these primordial objects, seeking to understand the universe's very first glimmer of light. Let us now allow our minds to wander into the realm of theoretical possibilities, contemplating the ingenuity of civilizations far more advanced than our own. Imagine a civilization that has outgrown the energy output of its home planet and seeks to harness the boundless power of its star. The concept of a Dyson sphere, first popularized by physicist Freeman Dyson, describes a hypothetical megastructure that completely encompasses a star, capturing nearly all of its radiant energy. This isn't necessarily a solid shell, which would be gravitationally unstable and require unimaginable amounts of material. More plausibly, it could be a quote 24, a vast constellation of orbiting solar collectors and habitats, forming a dense shell around the star. Such a structure would provide an unfathomable amount of energy, allowing a civilization to power its needs for eons. While purely theoretical, and certainly beyond our current technological capabilities, the idea of Dyson spheres offers a fascinating thought experiment about the ultimate limits of technological advancement and resource utilization in the cosmos. Scientists even occasionally search for signs of such structures, unusual infrared signatures that might betray a star radiating less visible light than expected, suggesting its energy is being harvested by an unseen megastructure. It's a testament to the universe's potential for grand designs, both natural and perhaps artificial. We have touched upon dark energy, the mysterious force accelerating the universe's expansion. Let us now delve deeper into the profound implications of this accelerating expansion for the ultimate fate of the cosmos. Our current understanding, supported by extensive observational evidence, points towards a future dominated by the Kabekengemra quote 25, also known as the Elandlai quote 26 of the universe. As dark energy continues its relentless push, galaxies will accelerate away from one another at ever-increasing speeds. Eventually, all but our local group of galaxies will recede beyond our cosmic horizon, becoming forever unreachable and unobservable, lost to an expanding void. Over trillions of years, stars will exhaust their fuel, collapsing into white dwarfs, neutron stars and black holes. These remnants will slowly cool, radiating away their last vestiges of energy. Black holes, the universe's ultimate gravitational prisons, will themselves slowly evaporate through Hawking radiation, a process taking timescales far exceeding the current age of the universe. In this distant, unimaginable future, the universe will become a cold, dark, and empty expanse, a dilute soup of fundamental particles, where all energy has been evenly distributed and no further work or processes can occur. It's a deeply contemplative, yet undeniably serene, vision of the universe's eventual tranquility, a cosmic stillness after billions upon billions of years of dynamic activity. Finally, let us consider the profound and often surprising influence of the universe's most formidable gravitational giants, supermassive black holes. Far from being mere cosmic drains, these colossal entities, residing at the centres of nearly all large galaxies, are not just passive observers but active architects, profoundly shaping the evolution of their host galaxies through a process known as quote Jaws 27, when a supermassive black hole actively accretes matter, forming an active galactic nucleus, AGN. Like the blazars we discussed earlier, it releases enormous amounts of energy in the form of powerful winds, jets, and radiation. This energy can heat and push away the surrounding gas and dust, preventing it from collapsing to form new stars. This quote 28 can effectively shut down star formation in a galaxy, regulating its growth. Conversely, during periods of less intense activity, the black hole's influence can also trigger star formation by compressing gas clouds. The delicate balance between these positive and negative feedback mechanisms is crucial to understanding why galaxies have the sizes, shapes, and stellar populations we observe. The supermassive black hole, though tiny in comparison to its host galaxy, acts as a cosmic thermostat, regulating the galaxy's temperature and star-forming activity, orchestrating a grand, slow dance of creation and suppression across billions of years. It's a testament to the intricate, interconnected nature of the cosmos, where the most extreme objects play a pivotal role in the grand narrative of galactic evolution. As we gently bring our focus back to the quiet space within you, we hope these latest insights into the universe's profound depths and its ultimate destiny have deepened your sense of wonder. The cosmos, in its grand design and its minutest details, continues to unfold its mysteries, inviting us to contemplate its vastness and our place within its serene, ever-expanding story. Let the echoes of these cosmic tales linger, soothing your mind as you drift into a peaceful contemplation of existence, as the colossal dance of supermassive black holes sculpts galaxies, regulating the very birth of stars with their powerful feedback loops. We gently turn our gaze from these cosmic architects to the more intimate, yet equally astonishing realms of planetary existence and the intricate tapestry of the universe's large-scale structure. We invite you to drift further into the boundless wonders, where the familiar laws of physics twist into breathtaking, often bewildering forms. Let the gentle current of knowledge carry you through these new revelations, a soothing experience designed not for retention, but for the quiet awe of discovery. Imagine a world where the very sky weeps not water, but molten iron, or where clouds of silicate crystals unleash a storm of raining glass. Such truly alien meteorology exists on distant exoplanets, pushing the boundaries of our terrestrial understanding. On some ultra-hot Jupiters, like the infernal WASP-76b, intense stellar radiation heats the atmosphere to such extreme temperatures that iron vaporizes, condenses on the cooler night side, and then precipitates as liquid iron rain, creating a glittering metallic downpour unlike anything on Earth. Other worlds, perhaps closer to the scorching embrace of their parent stars, may experience winds so fierce they churn up surface rock, creating airborne dust that eventually falls as a shower of small, sharp stones. And then there are the diamond planets, or those with atmospheres so rich in carbon that under immense pressure and heat, diamonds could form in their upper atmospheres, perhaps even raining down as precious, glittering jewels onto their surfaces. These celestial downpours are a stark reminder of the universe's boundless creativity, where the elements we know behave in spectacularly unfamiliar ways, crafting landscapes and skies utterly beyond our wildest terrestrial dreams. Beyond the individual galaxies and even their clusters, the universe arranges itself into structures of truly staggering scale, the cosmic web. Within this web, matter is not evenly distributed but forms vast interconnected networks of cosmic filaments and cosmic walls. These are the largest known structures in the universe, colossal tendrils of galaxies, gas and dark matter, stretching for hundreds of millions of light years, separated by immense, empty voids. Imagine an invisible scaffolding, a three-dimensional lattice where galaxies are strung like pearls along luminous threads, or clustered into shimmering sheets. These filaments and walls represent the very skeleton of the cosmos, the gravitational highways along which galaxies migrate and merge, driven by the unseen hand of dark matter. Our own Milky Way, along with billions of other galaxies, resides within one such filament, part of this grand, intricate design. Observing these structures is like looking at the universe's very bones, revealing the primordial patterns laid down in the aftermath of the Big Bang, a testament to the universe's elegant large-scale organization. Just as gravity can warp space-time and bend the path of light, it can also stretch light itself, shifting its wavelength towards the red end of the spectrum in a phenomenon known as gravitational redshift. This is a profound consequence of Einstein's theory of general relativity, demonstrating how even photons, massless particles of light, are affected by powerful gravitational fields. When light escapes from a region of strong gravity, such as near a black hole or a massive star, it loses energy as it climbs out of the gravitational, quote 29. This energy loss manifests as an increase in the light's wavelength, making it appear redder to a distant observer. Conversely, light falling into a gravitational well experiences a gravitational blue shift, gaining energy and appearing bluer. This subtle yet powerful effect provides crucial evidence for the existence of extremely dense objects and helps scientists probe the nature of gravity in the most extreme environments. It's a cosmic reminder that space, time, and light are all intricately interwoven, their properties mutable under the universe's fundamental forces. While we have marvelled at the spectacular final acts of massive stars in supernova, the universe holds an even more cataclysmic explosion in its repertoire, the hypernova. These are events of truly mind-boggling power, thought to be hundreds of times more energetic than typical supernova, marking the death throes of the most massive stars, those at least 25 to 100 times the mass of our Sun. When these colossal stars collapse, they don't just explode, they unleash a torrent of energy so immense that it can momentarily outshine an entire galaxy. Hypernovae are believed to be the origin of some of the most powerful phenomena in the universe. Long-duration gamma-ray bursts, which are focused beams of high-energy radiation that can travel across billions of light-years. The extreme conditions within a hypernova forge heavy elements in quantities far exceeding regular supernova, scattering them across the cosmos as the building blocks for future stars, planets, and perhaps even life. These titanic blasts are rare, fleeting glimpses into the universe's most violent and creative processes, a cosmic crescendo of destruction and genesis. As we explored the grand filaments and walls of the cosmic web, we noted the vast, empty regions separating them. The cosmic voids. These are not entirely empty, but rather immense, sparsely populated expanses of space, stretching for hundreds of millions of light years, where matter density is significantly lower than the cosmic average. Yet, even within these seemingly desolate realms, a few intrepid galaxies exist, known as void galaxies. These solitary wanderers are often smaller, bluer, and more actively forming stars than their counterparts in denser regions. Their isolation means they have largely avoided the gravitational interactions and mergers that shape galaxies in clusters and filaments. They are cosmic hermits, evolving in splendid solitude, unperturbed by the galactic cannibalism and tidal forces that dominate crowded environments. Studying void galaxies offers a unique window into galactic evolution in a pristine, undisturbed setting, allowing us to observe how galaxies might form and grow in the absence of external influences, a quiet counterpoint to the universe's bustling interconnected cities. our journey has led us to contemplate black holes formed from collapsing stars and the supermassive giants at galactic centers. But what if black holes existed even before the first stars ignited? This is the intriguing concept of Pyanti, primordial black holes. Theoretical objects that could have formed in the immediate aftermath of the Big Bang. In the incredibly dense and turbulent conditions of the early universe, tiny fluctuations in density could have become so extreme that certain regions collapsed directly into black holes, without the need for stellar progenitors. These primordial black holes could range in size from microscopic, perhaps even smaller than an atom, to many times the mass of the Sun. They are purely hypothetical for now, but if they exist, they could potentially account for some, or even all, of the universe's mysterious dark matter. They might also offer clues about the conditions of the very early universe, a fleeting epoch that remains largely hidden from our direct observation. The search for these ancient cosmic relics continues, a quest to uncover the universe's most ancient, enigmatic inhabitants. From the theoretical depths of primordial black holes, we now expand our perspective to our very own cosmic neighborhood, revealing a truly immense address, the Laniakea supercluster. Imagine a vast, interconnected web of galaxies spanning over 500 million light-years, containing approximately 100,000 galaxies, including our own Milky Way. The name Laniakea means immense heaven in Hawaiian, a fitting description for this gargantuan structure. Within Laniakea, galaxies are not randomly scattered. They are all gravitationally bound, flowing towards a common center of mass known as the Great Attractor, a mysterious region of immense gravitational pull. Our local group of galaxies, which includes the Milky Way and Andromeda, is merely a small component of this larger supercluster, gently being pulled along with countless others. This discovery, made relatively recently, transformed our understanding of our place in the cosmos, revealing that we are part of an even grander interconnected system, a colossal river of galaxies flowing through the fabric of space-time. It offers a humbling and awe-inspiring perspective on the universe's hierarchical organization. Amidst the grandeur of galaxies and the violence of stellar explosions, we often overlook the subtle, ubiquitous presence of interstellar dust clouds. These aren't merely mundane cosmic dirt. They are the fertile grounds for creation, the raw material from which stars, planets, and even the complex molecules necessary for life are forged. Composed of microscopic grains of silicates, carbon, and ice, these vast cold clouds drift through the spaces between stars, often visible as dark silhouettes against the glowing nebulae or the bright backdrop of the Milky Way. Within these dusty cocoons, gravity slowly gathers particles, forming denser clumps that eventually collapse to ignite new stars. More remarkably, these dust grains serve as cosmic laboratories, providing surfaces where simple atoms can combine to form surprisingly complex organic molecules, including amino acids, the building blocks of proteins. These molecular nurseries hint at the widespread potential for life throughout the universe, suggesting that the ingredients for biology are not unique to Earth, but are woven into the very fabric of interstellar space, patiently awaiting the right conditions to flourish. As we ponder the prevalence of interstellar molecules and the vastness of the Laniakea supercluster, with its countless galaxies, each teeming with billions of stars, the question naturally arises, where is everybody? This profound conundrum is known as the Fermi paradox. Given the immense number of potentially habitable planets in our galaxy alone and the sheer age of the universe, it seems statistically probable that intelligent life should have arisen elsewhere and perhaps even spread across the cosmos. Yet, despite decades of searching, we have found no definitive evidence of extraterrestrial civilizations, no signals, no artifacts, no signs of their presence. This silence in a seemingly bustling universe is deeply unsettling and endlessly intriguing. Are we truly alone? Or are there explanations we haven't yet considered? Perhaps the distances are simply too vast, communication too difficult, or perhaps advanced civilizations face a quote 33, a common obstacle that prevents them from reaching a detectable stage. The Fermi paradox invites us to contemplate our unique existence and the profound mysteries surrounding life's emergence and persistence, a quiet challenge to our understanding of the universe's ultimate purpose. As these questions linger in the quiet expanses of your mind, we hope this gentle journey through the wild and weird facts of space has offered a moment of serene contemplation. The universe, in its boundless complexity and enigmatic silence, continues to unfold its secrets, inviting us to wonder, to explore, and to find peace in its vast, intricate design. We leave you now to drift in the afterglow of these cosmic revelations, awaiting our next shared voyage into the depths of stellar marvels. As we continue our gentle drift through the cosmic ocean, let the currents of wonder carry us further into the unknown. We invite you to simply observe, to let these strange and beautiful truths about our universe wash over you like a calming tide. There is no need to grasp, only to experience the expansive peace that comes from contemplating the boundless ingenuity of existence. Each revelation is a star in a vast, quiet sky, shining for your tranquil exploration. Imagine stars, not bound by the gravitational embrace of their home galaxies, but flung outwards into the vast cold emptiness of intergalactic space, travelling at speeds so immense they escape their cosmic birthplaces forever. These are hypervelocity stars, celestial nomads ejected by the most powerful slingshots in the universe, supermassive black holes. Our current understanding suggests that when a binary star system, two stars orbiting each other, ventures too close to the colossal black hole at a galaxy's core, the intense gravitational forces tear them apart. One star might be captured, destined to orbit the black hole, while its companion is violently accelerated and hurled away, often at speeds exceeding 1,000,000 miles per hour. These solitary travellers are a poignant sight. If only we could perceive their lonely journeys. They streak across the cosmic canvas, leaving their galactic families behind, never to return. Their light, a beacon of a lost home, will eventually fade into the intergalactic void, a testament to the brutal yet beautiful dynamics that shape galactic centres. For eons they will be solitary points of light, traversing the immense distances between galaxies, perhaps encountering nothing but the faint echoes of the cosmic microwave background. Their existence reminds us that even stars, symbols of stability and warmth, can become wanderers, propelled by forces beyond imagination into an eternal, silent voyage. Galaxies, far from being static collections of stars, are dynamic, living entities, constantly recycling their very essence. This intricate process is often described as galactic fountains. a majestic cycle of cosmic respiration. When massive stars reach the end of their lives, they explode in spectacular supernovae, unleashing torrents of energy and matter. These cataclysmic events can blast vast quantities of gas and dust out of the galactic disk, sometimes hundreds or even thousands of light years above and below the plane where most stars reside. This superheated, energized gas forms colossal plumes, rising like ethereal geysers into the galactic halo. Yet, gravity, the universe's omnipresent sculptor, eventually reclaims this expelled material. As the gas cools and loses energy, it gradually slows its ascent and begins a slow, majestic descent back towards the galactic disk, like a gentle rain of cosmic dust and hydrogen. This returning gas then feeds new generations of stars, completing the cycle. Galactic fountains are vital for galactic evolution, regulating star formation, enriching the interstellar medium with heavier elements forged in stellar furnaces, and distributing them throughout the galaxy. It is a breathtaking dance of destruction and creation, a continuous breathing in and out that ensures galaxies remain vibrant, ever-renewing nurseries of stars and planets. In our quest for life beyond Earth, we often gaze towards exoplanets orbiting distant stars. Yet some of the most intriguing possibilities lie much closer to home, hidden beneath the icy shells of moons within our own solar system. These are the ocean worlds, celestial bodies like Europa, Enceladus, and Titan, which harbour vast liquid water oceans beneath their frozen exteriors. Despite surface temperatures far below freezing, internal heating mechanisms, primarily tidal forces from their massive parent planets, like Jupiter and Saturn, generate enough warmth to maintain oceans that could be deeper and larger than all of Earth's oceans combined. Imagine a world where the surface is a desolate expanse of cracked ice, constantly bombarded by radiation, yet beneath, in the perpetual twilight, lies a dark, warm, and chemically rich ocean. Hydrothermal vents on the seafloor of these moons could provide the energy and nutrients necessary for life, much like those found at the bottom of Earth's oceans. Enceladus, for instance, actively vents plumes of water vapor and organic molecules into space, offering tantalizing evidence of ongoing geochemical processes. These subsurface havens, shielded from the harsh realities of space, represent prime candidates in our search for extraterrestrial life, reminding us that life's resilience and adaptability might thrive in the most unexpected and profound cosmic cradles. As we journey from the grandest structures to the most fundamental aspects of existence, we encounter a concept so mind-bending it challenges our very perception of reality: the quantum foam. At incredibly minuscule scales, specifically the Planck length, an unimaginably small 10 to the negative 35th meters, quantum mechanics suggests that space-time itself is not smooth and continuous, but rather a turbulent, bubbling maelstrom. It's theorized to be a frothing sea where virtual particles constantly pop into and out of existence, and space-time geometry fluctuates wildly. This quantum foam represents the limit of our current physical understanding, a realm where gravity and quantum mechanics are expected to merge into a unified theory. In this microscopic chaos, the very fabric of reality is not fixed but undergoes incessant, ephemeral changes. It's as if the universe, when viewed with ultimate precision, is not a solid canvas but a shimmering, effervescent tapestry, woven from fleeting energy and fleeting geometry. While currently theoretical, the quantum foam offers a profound glimpse into the ultimate nature of existence, suggesting that even the emptiness of space is alive with a ceaseless, microscopic dance of creation and annihilation, a silent, unseen ballet at the very foundations of the cosmos. We have explored the universe's vibrant birth and dynamic evolution, but what of its ultimate fate? One prevailing theory, the Big Freezer said, or heat death, paints a picture of a universe that slowly, inexorably, approaches a state of ultimate cosmic void, a great nothing. As dark energy continues to accelerate the expansion of space, galaxies will drift further and further apart, eventually disappearing beyond each other's cosmic horizons. Stars will exhaust their fuel, dying out one by one, leaving behind stellar remnants like white dwarfs, neutron stars, and black holes. Over truly unimaginable timescales, even these remnants will fade. White dwarfs will cool into black dwarfs, neutron stars will dissipate, and black holes, through the incredibly slow process of Hawking radiation, will eventually evaporate, leaving behind only fundamental particles and photons. The universe will become an infinitely vast, cold and empty expanse, a dilute soup of photons and leptons where all energy is evenly distributed and no further work can be done. There will be no light, no heat, no structure, no change, just an eternal featureless void. This ultimate quote 35 is a profound and perhaps melancholic contemplation, yet it is a potential end woven into the fabric of cosmic laws, a silent testament to the universe's grand yet finite journey from singularity to ultimate stillness. Black holes, as we've learned, are cosmic enigmas, regions where gravity is so intense that nothing, not even light, can escape. But beyond the supermassive giants at galactic centers and the stellar mass black holes born from supernovae, there exists another, more elusive class: rogue black holes. These are individual black holes, often stellar mass, that have been gravitationally ejected from their birthplaces, perhaps during a chaotic galactic interaction or a multi-star system collapse, and now wander invisibly through interstellar or intergalactic space. Unlike their counterparts anchored in galaxies, these rogue black holes are incredibly difficult to detect. They emit no light of their own, and without a companion star to feed upon, they offer no telltale X-ray flares. Our primary method of detecting them involves observing their gravitational lensing effects. As a rogue black hole passes in front of a distant star, its immense gravity bends the star's light, causing a temporary brightening and distortion of the star's image. These transient events are rare and fleeting, requiring precise astronomical observations. The existence of these invisible nomads adds another layer of profound mystery to the cosmos, reminding us that countless massive, unseen objects might be silently drifting through the void, shaping the gravitational landscape in ways we are only beginning to comprehend. To conclude our journey through the truly wild and theoretical, let us contemplate Castor. Cosmic strings. These are not strings in the everyday sense, but hypothetical, one-dimensional topological defects that scientists theorize might have formed in the unimaginably hot and dense conditions of the very early universe, moments after the Big Bang. Imagine them as cracks or imperfections in the fabric of space-time itself, incredibly thin, yet potentially stretching across vast cosmic distances. If they exist, cosmic strings would be extraordinarily dense, perhaps thinner than an atomic nucleus, but with a mass so immense that a mere metre of string could weigh more than the Earth. They would carry immense tension, capable of ripping through space-time, and could potentially leave gravitational imprints on the cosmic microwave background, or cause subtle gravitational lensing effects on distant galaxies. While direct evidence for cosmic strings remains elusive, their theoretical existence offers a fascinating glimpse into the extreme physics of the infant universe, a time when the fundamental forces of nature were unified, and the very structure of reality was being forged. They are a whisper from the dawn of time, a potential relic of a primordial universe, reminding us that the deepest mysteries often lie at the very beginning of everything. As we gently recede from these profound and often startling truths, we hope you find a lingering sense of peace and wonder. The universe, in its boundless strangeness and intricate design, offers an endless wellspring of fascination. We invite you to carry this tranquility with you, knowing that the cosmos, in all its majestic complexity, continues to unfold its secrets, one gentle fact at a time, as we gently drift through the cosmic tapestry, letting the universe's grand narrative unfold around us. Our journey continues to reveal layers of astonishing complexity and profound energy. We've explored the silent dance of dark matter and the expansive push of dark energy, the birth and death of stars, and the intricate architecture of galaxies. Now, let us turn our gaze to phenomena that are not merely vast, but spectacularly violent and luminous, echoes of a time when the universe was younger, more tumultuous, and bursting with raw power. We invite you to simply absorb these next revelations, allowing their immensity to wash over you, a soothing current of knowledge in the vast ocean of space. Imagine a beacon so incredibly bright that it outshines an entire galaxy of hundreds of billions of stars, yet it emanates from a region no larger than our own solar system. These are quasars, short for quote 36, and they represent some of the most luminous and energetic objects in the observable universe. We understand them now as the incredibly active cores of distant young galaxies, powered by supermassive black holes greedily devouring vast amounts of gas and dust. As matter spirals into the black hole, it forms an accretion disk, heating up to temperatures of millions of degrees and emitting intense radiation across the entire electromagnetic spectrum, from radio waves to X-rays and gamma rays. The light we observe from quasars has often travelled billions of years to reach us, offering a glimpse into the early universe, when galaxies were still forming and their central black holes were hungrier, more active. Their immense brightness allows us to study the composition and conditions of the universe at these primordial epochs, acting as cosmic flashlights illuminating the intergalactic medium through which their light passes. Research indicates that the most powerful quasars can emit thousands of times the total energy output of the Milky Way, radiating with a ferocity that defies easy comprehension. They are not merely bright, they are cosmic lighthouses, piercing the darkness of billions of light years, whispering tales of the universe's tumultuous youth. Related to quasars, yet possessing an even more dramatic display of cosmic power, are blazars. These are a special type of quasar where one of the two relativistic jets of superheated plasma, ejected at nearly the speed of light from the vicinity of the central supermassive black hole, happens to be pointed almost directly towards Earth. Think of it as looking straight down the barrel of a cosmic cannon. This unique orientation causes a phenomenon known as Doppler boosting, where the emitted radiation is significantly amplified and compressed in our direction, making blazars appear exceptionally bright and highly variable across all wavelengths. The energy output from a blazar's jet is truly staggering, capable of producing some of the most extreme high-energy phenomena in the cosmos, including powerful gamma-ray bursts. The variability of blazars is fascinating. They can brighten or dim dramatically over timescales of days or even hours, a testament to the chaotic and energetic processes occurring near their central black holes. We are, in essence, observing the direct impact of a cosmic particle accelerator on a galactic scale, a direct conduit of energy from the heart of a distant galaxy straight into our telescopes. It's a humbling reminder of the universe's capacity for focused, overwhelming power, a spectacle both terrifying and beautiful in its intensity. As we expand our perspective beyond individual cosmic powerhouses, we encounter structures so immense they challenge our very notion of scale. Beyond the familiar clusters and superclusters, the universe organizes itself into even grander formations known as Great Walls of Galaxies. These are vast, sheet-like arrangements of galaxies, galaxy clusters and superclusters, stretching for hundreds of millions or even billions of light-years across the cosmos. They are the largest known structures in the universe, forming the, quote, 38 quote of the cosmic web separating immense empty voids. One of the most famous examples is the Hercules Corona Borealis Great Wall, a filamentary supercluster of galaxies that spans an astonishing 10 billion light-years, making it the largest known structure in the observable universe. The existence of these walls is a profound confirmation of our understanding of cosmic evolution, where gravity, acting over immense timescales, has pulled matter together into these vast interconnected networks. We see them as the visible scaffolding of the universe, illuminated by the collective light of billions of galaxies, each a star-filled island within this grand cosmic architecture. Contemplating these structures, we find ourselves enveloped in a sense of awe at the universe's intricate, large-scale organization, a silent testament to the enduring power of gravity and the initial seeds of cosmic structure laid down in the early universe. Not all stars live out their lives in the gentle embrace of their birth clusters or the steady rotation of their galaxies. Some are cast out with astonishing force, becoming hypervelocity stars. Celestial nomads hurtling through interstellar space at speeds so extreme they can escape the gravitational pull of their entire home galaxy. We've observed these stellar outcasts travelling at speeds of millions of miles per hour, far exceeding the typical velocities of stars within the Milky Way. The leading theory for their ejection involves the supermassive black hole at the centre of our galaxy, Sagittarius A star. When a binary star system, two stars orbiting each other, gets too close to this colossal black hole, the black hole's immense gravitational forces can tear the binary apart. One star is captured into a tight orbit around the black hole, while its companion is slingshotted away at incredible speeds, destined to wander the intergalactic void alone. These rogue stars are a stark reminder of the violent dynamics hidden within galactic cores, where the serene appearance of a spiral galaxy belies the powerful gravitational interactions occurring at its heart. They are cosmic arrows, shot from the galactic center, each carrying a silent tale of a violent encounter with the universe's most extreme gravitational engine. Journeying back in time, we encounter a pivotal period in cosmic history known as the Rhionization epoch. Following the Big Bang, the universe was a hot, dense plasma. As it expanded and cooled, electrons and protons combined to form neutral hydrogen atoms, rendering the universe opaque to light, a period known as the Cosmic Dark Ages. But then, about 150 million to 1 billion years after the Big Bang, something profound happened. The universe began to light up again. This reionization was driven by the first stars and quasars. These nascent massive stars burned fiercely, emitting intense ultraviolet radiation that began to strip electrons from the neutral hydrogen atoms, reionizing the intergalactic medium. It was a gradual process, like a fog slowly lifting, transforming the universe from a dark, neutral expanse into the transparent, ionized cosmos we observe today. We can detect the faint echoes of this epoch through observations of the cosmic microwave background, and by studying the most distant quasars whose light has traversed this reionizing fog. The reionization epoch was the universe's grand awakening, a transition from cosmic infancy to the complex luminous structure we explore, a reminder that even the most fundamental properties of the universe, like its transparency, have evolved dramatically over cosmic time. We've discussed rogue planets and hypervelocity stars, but the universe also harbours a more elusive and chilling type of wanderer: rogue black holes. These are black holes that have been ejected from their home galaxies or clusters, or perhaps formed in the early universe and never settled into a galactic core. Unlike their supermassive cousins anchored at galactic centres, these stellar mass or intermediate mass black holes are free-floating, invisible, and incredibly difficult to detect. Their presence is often inferred rather than directly observed. We might detect them through their gravitational lensing effects, where their immense gravity distorts the light from background stars, temporarily brightening them as the black hole passes in front. Scientists have theorized that billions of these rogue black holes could be drifting through the Milky Way alone, remnants of stellar collapses or binary interactions silently traversing the galactic plane. These invisible titans present a unique cosmic hazard, a testament to the universe's capacity for hidden, powerful forces. Their existence adds another layer of mystery to the cosmic web, reminding us that much of the universe's mass and many of its dramatic players remain unseen, their presence only hinted at by their profound gravitational influence on the visible cosmos. Our journey through the cosmos often brings us face to face with the strange and beautiful implications of Einstein's theory of general relativity. One such implication is gravitational redshift, a phenomenon where light or other electromagnetic radiation loses energy as it climbs out of a gravitational well. As light escapes a massive object, like a star or a black hole, its photons expend energy to overcome the gravitational pull. This loss of energy causes the light's wavelength to stretch, or quote 39, meaning it shifts towards the red end of the electromagnetic spectrum. More profoundly, gravitational redshift is inextricably linked to time dilation. In regions of stronger gravity, time itself slows down relative to regions of weaker gravity. For an observer far from a massive object, Light emitted from near that object appears red-shifted because the quote 40th of the clock emitting the light appear to slow down. This effect has been precisely measured, notably in the light from white dwarfs, which possess incredibly strong gravitational fields. It's a subtle yet profound demonstration of how space-time is not a fixed stage but a dynamic, malleable fabric, warped and stretched by mass and energy. The universe, in its very essence, is a symphony of interconnected forces, where even the passage of time and the very nature of light are influenced by the invisible scaffolding of gravity, inviting us to contemplate the deep elegance of its fundamental laws. As we continue to navigate these cosmic wonders, we hope you find a quiet solace in the immensity and intricacy of it all. There is no need to grasp every detail, only to allow the wonder to settle, gently expanding your sense of what is possible, what is real, and what remains a beautiful, shimmering mystery in the grand, unending story of the cosmos.